In this lecture set, we're going to be discussing hierarchical linear modeling, which is an extraordinarily useful form of, I guess you could say, regression that is used in a variety of different social and practical data situations. Within this lecture set, we're going to be discussing a review of a wide variety of basic regression and ANOVA concepts. We're going to discuss the context in which we use these particular models. We're going to discuss the models themselves and what's involved with them. We're going to discuss how to interpret hierarchical linear models, which itself can be an extensive process. We'll discuss some extensions, and then we'll close out with implementing HLM and the SPSS software. All right, so let's start with reviewing fixed versus random effects. So you may have seen this when you learned about ANOVA the first time. And for context, in our ANOVA, analysis of variance, remember in ANOVA, independent variables are categorical. Each of the independent variables has different groups. So maybe my independent variable is your favorite ice cream, and the different options for the independent variable, which are called factor levels in ANOVA, but we'll just call groups. Could be my favorite ice cream is chocolate or vanilla or strawberry. Now, these groups were either selected specifically, in which case we'd consider them fixed effects, or these groups were selected randomly, in which case we consider them random effects. What I mean by this is, let's say we're at a company who is looking at implementing a variety of different marketing strategies. Now, the company can either ask two questions. One, it can say, look, I have three marketing strategies I'm actively considering. I care about these three because these are the three that we've designed, and I need to figure out which of these three is the best. And in that particular case, we specifically care about those three and want to pick the best one. That would be considered a fixed effect. On the other hand, I could be trying to justify a marketing budget as a whole and saying, hey, does marketing really matter here? I don't particularly care what marketing methods I test. I just need to test a variety of marketing methods and see if that has an outcome on the return on investment or whatever. So in this particular case, I don't care about the marketing method specifically. I just want to try a bunch and see if that has an impact on my outcome. So for example, data from 100 companies, you would either throw away all of them except for the ones you care about. In this hypothetical case, I care about two, because it doesn't really make sense to study all marketing methods. My company just has two. Or if I have 100 companies, it doesn't make sense to study all of them. I just care about the two that are mine. And if that's the case, then you would consider that to be a fixed effect. On the other hand, if you accounted for all of these to get a better prediction of the company effect, then this would be considered a random effects model. All right, now let's talk about regression. I'm sure you've seen regression before. The basic regression equation can be given as y equals beta 0 plus beta 1x plus beta 2, beta 3, beta 4, etc., all the way out till we have a certain number of variables. Y is the outcome variable. Beta 0 is the intercept. That is the value of y when all of the x's are at 0, and this is important. We'll be leaning on this later. Beta sub j is the slope for the jth variable, x sub j. So in this particular case, beta sub 1 would be the slope for the first variable. And by slope, what I mean is that as x increases by 1, x1, the first variable, the change in the outcome, y, will be whatever beta is. So x increases by 1. If y changes by 0.5, then beta is going to be 0.5. It's going to represent how much y changes when x changes by 1 unit. And last but not least, we have the unexplained variance in the outcome. The outcome variance that's not explained by the model, and this is called epsilon. And we consider this to be an error term for the participant. That is, how much of the variability in the participant's response was not captured by our statistical model. Now, there's an additional term that we can add in regression, and that is called an interaction term. So interaction terms assess the effect that one independent variable has on a second independent variable's relationship with the outcome. So for an interaction term to be possible, I will need to have two independent variables. And pretty much what I'm looking at is, does one change how the other one works? Sometimes this is called a moderation effect. Interaction terms are created by simply multiplying the two independent variables together, and I can have interaction terms with more than two independent variables, but I would multiply as many terms as I have. I'll just pick two independent variables together, and I literally times them together and include that product as an independent variable. Product is just the result of multiplying things. So I literally multiply them together and include the result in the model as a new variable. So for instance, in a hypothetical regression case, I have an independent variable x sub 1, an independent variable x sub 2, and I multiply them together, x sub 1 times x sub 2, and I literally mean multiply each value. Each person's x1 score gets times by each person's x2 score, and I include that result as a new variable called x sub 1, x sub 2. Now, what's interesting about this is when I include the interaction term in the model, there's a couple of things that happen to not the interaction term, but what we call the main effects. That is, I have the interaction between x1 and x2, that's beta 3. The main effect is x1 and x2. The betas for, well, beta 1 for x1 and beta 2 for x2, those are called the main effects. And so in this case, if the interaction is significant, the main effects aren't interpretable as is. Ultimately, the presence of an interaction means that the interpretation of the relationship between the independent variable and the dependent variable is different depending on what the level of the other variable is. That is, I can't just say x1 is related to y if there's a statistically significant interaction with x2. It really depends on what the value of x2 is. And that's actually the whole definition of the interaction, is that the relationship between x1 and y depends on x2. And similarly, the relationship between x2 and y depends on x1. So if there's a statistically significant interaction, that means that the interpretation of x1's relationship with y and the interpretation of x2's relationship with y just became a lot more complicated, because the interpretation of x1's relationship with y depends on x2, and x2's relationship with y depends on x1. Now, I want to be careful. That doesn't mean we can't do any interpretations, just that we can't interpret it from the regression output as is. Normally, what we would draw is something called an interaction plot, and that lets us interpret these a little bit more robustly in the context of the other variables. The other thing that happens that we don't always talk about is if the interaction is not significant, and frankly, even if it is significant, it doesn't really matter if it's significant or not. The main effects for the variables included in the interaction only are interpreted when the other variables included in the interaction are 0. So what do I mean? Let's consider beta 1. Normally, the interpretation of beta 1 without the interaction in the model is as x1 changes by 1 unit, this is how much we expect y to change after accounting for x2. That's the typical interpretation. With the interaction in the model, whether or not the interaction is statistically significant, the interpretation of beta 1 has now changed. The interpretation of beta 1 is now when x1 increases by 1, This is beta 1 is how much we expect y to increase when x2 is 0. And it's when all the other things that x1's interacted with are 0. In this case, that's x2. The same thing happened with x2. Beta 2 now represents, as x2 increases by 1, our expected change in y, not after accounting for x1, but at a very specific point of x1. That is when x1 is 0. And that can drastically change the interpretation of our regression parameter estimate. So it's important to realize that by adding a regression, first of all, if the regression is significant, you can't interpret the main effects as is anyway. But even if the regression is not significant, you have to be careful because the main effects now have a very specific interpretation, and that is they're interpreted when the other independent variable is 0. And that's something that wasn't the case before the interaction term was included. Now, I'll be frank, this can actually be a really irritating feature of including variable interactions. And so we need to, in some way, account for this. And one of the ways that we can account for this is through the concept of centering. Centering is the process of moving independent variable to have a mean of 0. Often we can move it to be at its variable mean. I mean, it literally is, if you think about taking all the data, picking them up and moving them as is. We kind of leave the distribution the same. We just move them so that the middle of the data fall in a different place. And that way, the goal is ultimately to make the value of 0 more interpretable. So in this particular case, we're going to have the value of 0 be the mean. And that's often the case, but it is important to note here that the value of 0 could be something different than the mean if we wanted it to be. So we could have a variable centered around a particular value of interest. So maybe I want to, I don't know, I won't come up with a hypothetical example. I'll just say we very, 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 very often move it to the variable mean, but we could center to something else if we want to. So if somebody says they centered, you can usually assume they centered to the variable mean. But in certain circumstances, it's really nice to be able to move this not to the variable mean, but to a completely different value. All right. So the calculation for the centered variable is really simple. You just take the original variable and you subtract what you want the new 0 to be. So in this case, we subtract the mean, and now for the centered variable, 0 represents a mean score on x. If we subtracted, I don't know, say 28, 0 would represent a score of 28 on x. So we can center around really whatever we want, as I mentioned earlier, just by subtracting that number. And again, the most common by far option is to subtract the mean from the variable. Note that this changes the meaning of a magnitude. An x value of 1, that is, no longer means x equals 1. An x value of 1 now means 1 bigger than the mean. But the change in magnitude doesn't change. That is, a 1 unit increase now means exactly the same thing as it did before. So the change in magnitude is something that stays the same. Single unit increases are important to stay the same for regression so that our interpretation of the parameters stay the same. So in a regression without an interaction, centering the variable affects the intercept, because remember, intercept is interpreted as the value of the outcome when the independent variable is 0. So earlier it was when the actual independent variable itself is 0. Now, if we center around the mean, value of the centered variable being 0 represents the original variable's mean, and the intercept is the effect of the outcome when the independent variable is at its mean, if we included the centered variable. So that's what happens without the interaction. But note that this doesn't affect the slope. The slope is as the variable increases by 1 unit, what happens to the outcome, and an increase in 1 unit with the original variable is the same thing as an increase in 1 unit in the centered variable. And again, this is an important thing, that we did change the magnitude, but we didn't affect the change in magnitude. That is, as you increase by 1, you are increasing by 1 on both the centered variable and the non-centered variable. Regression model with interaction, this change affects how the main effects in the slope interpretation are made. So as before, I mean, it doesn't really change the interpretation in that the interpretation of the parameter estimate for the coefficient of x1 is still when x2 equals 0. But if you center x2, now x2 equals 0 isn't the original variable equal to 0. Now the centered x2 equals 0 means when the original x2 is at its mean. And that might be much more interesting and interpretable than interpreting when the original variable is at 0. So that can be very, very, very helpful. It's important to know that this change isn't going to impact the interaction. It's just going to impact the interpretation of the slope of the other variable. So if I center variable 2, it's going to impact the main effect of variable 1's interpretation. If I center variable 1, it's going to impact the main effect of variable 2's interpretation. And it'll also impact the intercept. As a rule of thumb, it's always a good idea to center when you have an interaction term. And there's a decent argument to be made that maybe you should just always center your variables. Why is that? Well, frankly, because centering gives you a more usable intercept. Even a regular simple regression, no interaction. The intercept, assuming all the independent variables are 0, is often something that we look at and roll our eyes and say, oh yeah, we can't interpret that at all. But now, when the independent variables are at their mean, if you use the centered versions, well, maybe that is interpretable. Maybe that does give you some useful information. And this is nice because it doesn't have any cost in terms of the interpreting of the slope. So it gives you a more interpretable intercept with the same interpretability for slope. And all you have to do is subtract the mean from your variable. So that can be quite a nice feature of the centering. And again, you should really, really do it. If you have an interaction term, you should be careful to do it. But even if you don't have an interaction term, you may strongly consider doing it anyway to give you a more usable intercept. I guess the downside is, well, there's no real downside. There's really no reason not to do this unless the independent variable of 0 equals 0 for the original variable has a very strong and important meaning to you, which is almost never. So as a default, you probably should center your variables in regression. All right, statistical assumptions. So in a multiple linear regression, we make a bunch of assumptions about the error term. And ultimately, these assumptions are what led us to hypothesis testing and create confidence intervals, et cetera, everything that connects to our statistical distributions and some of the things that allow us to get the line of best fit. The main assumptions can be remembered in an acronym of LINE. L stands for linear, and that is that the relationship between the independent variables and dependent variable is linear. And as you can probably, as you've probably seen, we can have curves, but even then, the relationship between the independent variables and dependent variables should be linear after accounting for the curve in the model. Independence, so that's the I, that is observations are not related outside of the model. Students don't often think about this, but independence is an assumption. This whole outside of the model thing in parentheses there is actually kind of important. So think about something as simple as a t-test. When we consider our data are independent for an independent samples t-test, and let's say I'm comparing men and women on math ability. In that particular comparison, in the independent samples t-test, we aren't assuming all of our participants are completely unrelated. Far from it. Actually, in that study design, we're assuming that the men are related to each other And the women are related to each other, and that's how we're making the groups for the t-test. So even when we say independent samples here, we are saying independent, but independence is after accounting for the groups that we've already planned on. So when we talk about independence as a statistical assumption, independence is independence after accounting for the relationships that are built into the model. We don't break math by assuming men are related to men in a t-test versus men and women, or by assuming women are related to women and those scores might go together. That doesn't break math here. And again, it doesn't because the relationship is included in the model. And it's important to realize here, independence, sometimes it's referred to as unrelated errors or uncorrelated errors. All right, normality. Normality, ultimately, that the errors are distributed according to normal distribution. And then our last one, E, equal variance. Errors have a constant variance. Sometimes you'll hear this listed as homogeneity of variance or homoscedasticity, but LINH doesn't make a cool acronym, so I just use equal variance, LINE for equal variance. So in previous courses, you've probably talked through how to address number 1, 3, and 4. Linear, I mean, we add in like a squared term or a cubic term, and we can create some curves in there. Number 3 and 4, normality and variance, we often try transformations. But 2 is a little bit different. Independence is ultimately a design issue, and when we're assessing independence, often I'll look at the study design to determine are the participants randomly sampled, are there things that could connect participants in a way that aren't currently included, etc. So independence is actually a design issue more than it is well, independence is actually a design issue and often needs to be addressed directly and isn't something maybe you've ever dealt with or addressed before. All right, coefficient of determination. So the coefficient of determination, also called R squared, is something that we can use to estimate the percent of variance in one of the variables explained by the other. As far as the review goes, what I really want you to get are the basics of these equations. And that is that to calculate a percent variance explained style statistic, what I do is I take the sum of squares attributable to one component of the model and divide by the total sums of squares, or the variability contributable to one component of the model and divide by the total variability. So this is something that is relatively straightforward to calculate, but is important to conceptualize in that in this particular case, sums of squares of regression is the variability explained by my model, and the denominator, the bottom, sum of squares regression plus sum of squares total, or sum of squares error, is actually the total amount of variability in the model. So those are the only two components in there. And I take the variability due to this one component, divide by the total variability, and that's how I get something that says percent of variance is explained, is I actually physically calculated the percent of variance that was explained. In this case, again, both of these are the percent of total variation. These are really the same equation. All that's being indicated in the denominator is just that sometimes we can break that sum of squares total, the total variance, out into its different components and add them together. And in fact, that's very common to do. And when we end up using this later in this lecture, that's the approach we'll take. All right, well, this has been a review of a variety of different things, primarily focusing on regression, getting us prepared to enter hierarchical linear modeling.